Oh God, I have to tell you a joke. Sorry about that. It just came into my head. Right. Texan goes to Scotland on holiday. He's driving through the Highlands and he sees this tiny little Scottish village with one pub in it. And everybody in the town, that tiny little town, was queued up outside of the pub. So it gets his curiosity and he stops and he goes and the doors are open and he sees the barman inside cleaning glasses. And so he walks in and he goes to the barman and says, is the bar open? He says, yeah, it's been open for hours. And he says, oh, okay. And so he sits down and he notices the prices. And it's like a whiskey is 3 cents and a pint of beer is 4 cents. And he says to the barman, are they real prices? Oh, and the barman says, oh, you're looking at that. That's a special promotion. Today, it's 100 years since the bar was open. So we decided to charge the prices that were there 100 years ago. So 4 cents for a pint and 3 cents for a whiskey. And the Americans, oh, that's great. It says, I would like a treble whiskey and 2 pints of beer then. Barman gives him his drink and he's drinking away and he's looking round and the place is still empty. So the American says to the barman, where is everyone? And he looks at him and says, oh, they're all outside. They're waiting for the happy hour to start. Happy hour. Reduced prices. Oh God, that one died a death. I think it's funny. Right. Maggie, you're the only one that I can see you laughing. So, okay, we'll take that as you got the joke, right? Last joke then. Englishman is driving through the Highlands in his big fancy Rolls Royce and he gets to a set of traffic lights and he stops and he looks and he sees these 2 guys eating grass. And he rolls down his window and he says to him, what are you doing? And the 2 guys turn around and say, look, we're poor, we've got no money, we're starving, we're eating grass. And the Englishman said, oh, I can't have that. He says, you get into the back of my Rolls Royce, 2 miles up, I've got a big manor, big mansion, 2 miles up, I'm taking you there. And so they're driving along and the Englishman turns around and says, don't worry, guys. He says, 1 mile up the road, you're going to be at my new big manor. Says the grass is this tall.
Sounds messed up. I like it.
Okay. Let's get really started. There's a very small topic that we need to do. This is basically the intro, so I've been kind of skipping by it, but there's not too much in it. Hopefully you are looking at determine the points where a function is continuous. Good. Right. Continuity in a multivariate function is pretty much the same idea. A function is continuous in any point where you can actually get an answer, right? So, you know, like 1 over x has a problem at x equals 0, right? That kind of thing. But everywhere else, it's okay. So if you're looking at question 8, you've got xy in the top and this guy here on the bottom, okay? And they're asking you where this function is continuous, right? Well, if I look at the bottom expression, if that was ever 0, wouldn't we have a problem? If the entire bottom came to 0. But let's figure out if that's even going to happen. Would you agree that e to the power of anything is a positive number? E to the power of a billion, e to the power of negative a billion, right? You're never going to get 0 out of that, or even a negative number. So the bottom is totally fine. And would you agree that xy can't cause any damage? 5 times 2 is not going to do it. So the answer is that this function is continuous everywhere. And that, do you see that little r squared? That's just a 2-dimensional version of x's by y's, right? R times r. Now, let's look at a function like this one. Would you agree that the cosine is not the problem? The problem is this guy inside the square root. won't this function only exist and therefore be continuous when the thing inside the square root is greater than or equal to 0? So I just need to figure out when is 1 plus x minus y greater than or equal to 0. And I'm going to write that down because I'm not quite sure myself from the choices they've got what that's going to look like. So let me back here and show you my calculation. It would have been nice if they had just said, you know, that, right? Because then it would have been easy, right? But the choices I can see are not that. So they're all in terms of y being greater than. So here we go. If you subtract an x and subtract a 1 from both sides, you get that. And if you multiply everybody by -1, do you notice that the inequality sign switches around? Wow. Early 141. Remember doing that in 141 right at the start? If you multiply both sides of an inequality by a negative number, you reverse the direction of the inequality. That particular one I'm looking at would be the second dot. So that's your answer, right? It's that one. Now, the next one, the last one, is made up of 2 distinct pieces, right? And I want to know, when is this function, when does it exist, right? Because where it exists is where it's going to be continuous. So if you use this guy, doesn't x have to be greater than or equal to 0? Now, if you use this guy, doesn't 16 take away x squared, take away y squared have to be greater than or equal to 0 as well? But I'm looking through the list and none of them look like that. So I'm going to have to do some surgery, I guess. I'm going to subtract 16 from both sides. And then I'm going to multiply both sides by -1. And now I get that. So as long as x is greater than or equal to 0 and the x squared plus y squared is less than or equal to 16, you would be able to evaluate this function. And that one happens to be the first stop. Are you comfortable with that? So when they're talking about continuity, couldn't they just say, tell me the domain? Because aren't they going to be the same thing? A function is basically, these functions at least are continuous on their domain. And that is the end of 14.2. Now we get on to the good stuff. I believe it's 14.3. Let me double check. We are going to look at partial derivatives. If you choose to do Calc 4, you are going to be spending a lot of time calculating what are called partial derivatives. It's essentially, how do you differentiate a multivariate function, right? So suppose I have a function like f of xy, and it's x squared plus 2x plus 4xy plus y cubed, right? And I could put that into GeoBra and see what it looks like, right? Suppose I got that function. It's also sometimes written using this notation. I don't think that's a big deal. Would you agree that just different ways the same thing? How do you differentiate them? Well, here's the problem, and it's quite a big problem. Aren't there 2 variables here? But our idea of derivatives is that you differentiate this thing with respect to x, right? Or you could differentiate this thing with respect to y. So how does that work? Well, we have an idea or a thing called partial derivative. And this is the notation that we use. It's not your solid D, right? It's that, right? It's the kind of curved D, you know, the ones that look like that. And this is called the partial derivative of f with respect to x. And this is how you do it. You differentiate everything using x as a variable. Any other number or letter, in this case y, treat it as a constant. Treat it like it was 42. So let's see how this one works. If you differentiate x squared with respect to x, the partial derivative, you get 2x. Done. If you differentiate 2x, you get 2. Done. Well, that's good, isn't that just like you would expect it to be? Now it gets a little bit weird. If you differentiate 4xy and you do a partial derivative with respect to x, you get 4y. Now, what do you think you get when you differentiate y cubed with respect to x? Think of that as a constant, like 42 cubed. What would you get if you differentiated it?
0.
0. That was it. That wasn't too weird, maybe. Intuitive, does that kind of make sense that if you want to do a derivative, you have to pick a variable? And if you're going to pick one variable, you have to think of everybody else as not being a variable anymore, right? They're all being treated as if they were constants. So as long as you know how to do that, you know, in your brain, you're good to go. There is, however, a little notation issue. That is also another notation for this guy, right? Me personally, I like this notation because I'm lazy. Would you agree that involves writing more things? But that's the only difference. Now, I'm about to do the partial derivative with respect to y. Okay. If you differentiate x squared, won't you get nothing? If you do a partial derivative 2x, won't you get nothing? What will you get here when you differentiate with respect to y? So what would you get from 4xy if you do a partial derivative with respect to y?
4x.
Great. And what about y cubed? What would you get for y cubed?
3y squared.
3y squared. And I'm not going to rewrite the two notations a lot, right? Would you agree that the partial derivative with respect to x of a function and the partial derivative with respect to y of a function, there's no reason in the world they should be equal? Would you agree that in fact, would you agree that most of the time, aren't they going to be different? And that's totally okay, because they are. Now, if you're trying to think, what on earth is a partial derivative like these getting me? I want you to imagine, because I can't draw, right? These are like contour lines. Can you imagine that is what f of xy looks like, right? That's what that looks like, right? If you do a partial derivative fx, right? What you're doing here is that you're making y like it's a constant. So when you draw shapes in 3D, the x-axis comes out this way, the y-axis comes out this way, and the z-axis goes that way. It's a slightly weird orientation, but it has to be done that way because we use a thing called the right-hand rule, and you'll have to blame engineers for that because, you know, they do that funny thing with their fingers. Right? Evidently, that's the way we have to orient it. Now, if you are doing the partial derivative with respect to x, you're saying that y is constant. So can you imagine that you're taking a shape and you're slicing it parallel to the x-axis. Now, every time you cut that guy, so you imagine this surface being cut. If you cut it, let's say it here, wouldn't the shape look something maybe like this? Wouldn't you just get a curve? Right? So if you take a solid and you cut it at y equals 1, or y equals 10, or y equals anywhere, you get a curve. You are finding the slope of the tangent line to this curve at whatever point you happen to be interested in. So that's what this guy is calculating. It's calculating the slope of a tangent line to a slice of a solid shape at any given point, right? I know if that helps you understand what you're doing. It probably doesn't, but does at least it tells you why you're doing what you want, right? Now, if I was doing a shape in 3D world, which again I can't draw, would you agree that even in the 3D world, there are hills and valleys? And wouldn't it be a good idea if we could find out where the hills and valleys were, right, algebraically? Now, what do I know about a hill, for instance? Well, if you cut it parallel to the x-axis, or you cut it parallel to the y-axis, won't you get a slope that's 0? So what you are going to do is you're going to find out when are these partial derivatives 0. And whenever both of them are 0, you're looking at a hill or a valley. Isn't it a bit like f dash x equals 0? And that's how you find hills and valleys in Calc 1. So we have a mathematical way of finding on any function, because basically a function in 3D is like the skin of a surface, right? It's just the outside. We can find it by using partial derivatives. Okay, so what's our goal? Our goal is to do as many different functions as I can possibly cover and get used to finding partial derivatives, because it's a bit like Calc 1 in 2 days. Right, so you're going to see lots of derivatives. So I'm going to start off the nice baby one. Here is our function, and it's an x to the 4 plus 8x y cubed, right? And we're going to find the partial derivative fx and the partial derivative fy. In the book, they call it that. But most textbooks don't bother. They just call it this, right? Right. If you differentiate with respect to x, you get 4x cubed. And if you differentiate this with respect to x, you get 8y cubed. Are we comfortable with that? Right, now let's do it with y. What would you get from the x to the 4th term? Partial derivative of y. What would you get with the x to the 4th term?
0.
2? I'm not sure where that comes from. Do you get anything when you differentiate that with respect to y?
No, you get 0.
You get 0. Okay. What about this guy with respect to y? Think of x as just like 4. So it's like 84y cubed, right? What would you do? Per row? Right, with respect to y? 24 x y squared. That gets you nothing with respect to y. That gets you 3 times 8, 24 xy squared. Do you notice the x's is just tagged on like it was a number? Okay, let's try this fella. Partial derivative with respect to x. Okay, So that basically is like a number. So multiply by the power and reduce it by 1. Partial derivative with respect to y then. Treat that as a number and differentiate this. Are we good? Okay. Let's just move up the food chain. What about changing some variables while we're at it? And let's find the partial derivative with respect to x. So it's the natural log of this guy. Now, if you want to differentiate with respect to x, you get 1 over that guy. Great. Differentiating the natural log gets you 1 over the thing. Now, technically speaking, shouldn't it be times the derivative of what's inside, right? But isn't the derivative of this just 1? So that's finished. Now be a little bit more careful about this fella. Well, if you want to differentiate this function with respect to t, you're going to get 1 over the thing times the derivative with respect to t. That'll get you nothing. That's just like a number. And that'll do a power roll. Then you make it look pretty. Are you comfortable with that one? We're not changing the rules of Calc 1, right? We're still differentiating. All we're doing is identifying one thing as a variable and treating everything else as if it was a number, a constant. And that's kind of the rule of the game here. If you stick to that, you're going to be fine. Well, here's a function. If I want to differentiate this function, it just makes more sense that I write it like that. Agreed? Just easier to differentiate. Now I want to find the partial derivative with respect to u. So we're using that notation. Well, if you differentiate this expression with respect to u, isn't it a bit like 5u? All you get is that, because that guy gets you 1. And then I would probably do a style point, make it look like the original. If you wanted to do the partial derivative with respect to v, then power rule. Multiply by the power and reduce the power by 1, and then do some style point on it. And that's you finished. Any questions so far? I mean, there is a lot of functions that you know how to differentiate. So you should be able to differentiate similar looking functions with 2 variables in them. Okay, that one looks scary, but it isn't really. Right. Differentiate this with respect to x. So you're going to do a chain rule. It's going to be 100, this guy, to the power of 99, followed by the derivative of the inside function, right? This guy. Now, the derivative of this guy with respect to x is a 2x plus a y. And there are not an awful lot of style points, but you normally write things down from the simplest to the ugliest. So that would be the answer. If you want to do a partial derivative now with respect to y, it's also a chain rule. it's 100 x squared plus xy to the power of 99 times the derivative of the inside function with respect to y. Well, that gets you nothing, and xy just gets you x. Right, differentiate xy with respect to y, you just get an x. And so tidying up, it looks like that. Okay, I'm going to give you 5 questions and let you have a shot at them. I think practice makes perfect. So for each one of them, find the partial derivative with x and with y. Okay, you got 10 minutes. It's 1 minute for each one. Okay, it might not be 10 minutes, but hopefully I've given you enough time to get about 3 or so done. Let's get this show on the road. So if you want to do a partial derivative with respect to x, think of this as being x squared plus 2x times a number plus a number squared. So differentiate x squared, you get 2x. 2x times a number, well, you just get 2 of the numbers. Differentiate a number squared, don't get anything. Move on to this one. This is a number squared, so its derivative is 0. This is to a number y, so if you differentiate with respect to y, you get 2 lots of the number. And this is y squared, and if you differentiate, you get 2y. And have you noticed something quite unusual about these two answers? They are the same. Interesting. It's quite rare. But if a function has got symmetry to it, do you see it's kind of balanced, then that sometimes can happen. Pretty rare, but it can happen. Did you notice that this one needs a quotient rule? And not just your everyday nice quotient rule, a new kind of quotient rule, because you know there's a variable and there's a constant, and it's not always obvious who is who, right? But the formula for quotient rule is f dash g take away f of g dashed over g squared. Agreed? Now, if you're doing a derivative with respect to x, the derivative of this guy with respect to x is just 1. Leave the g alone. Take away, leave the top alone, and differentiate the bottom with respect to x. That's like x take away a number. So when you differentiate, you just get 1, and the whole thing on the bottom squared. So I get an x take away y minus an x take away y, like that, all over x minus y squared. And we end up with that guy, I hope. Does that look right? Okay. Now, if you go the other way, it's going to look similar, but it's not going to actually be the same. So, derivative of this guy with respect to y, well, it's a number plus y, so you get 1. Leave that guy alone. Take away this fella on his own, untouched. And if you differentiate that guy, you get a -1 all over x minus y squared. And so I get an x take away a y. A negative of a negative is an add, so you can add x add y all over x minus y squared. And I believe in this case, it's the x's that survive. Are we good with that?
Shouldn't the first one be a positive 2y?
This up here, let's check. Negative, negative, still negative. Check that it came from here. One of these, yep. Minus one of those, yep. Nope, negative 2y looks good. So there's a sign difference in these two as well, isn't there? One's plus and the other's negative. It's worth pointing out to me because I do make mistakes, but not this one. All right, this fella with x's gets you 2x sine y minus a number, derivative of a number, don't matter. If you differentiate a number sine y, you get a number cos y, and differentiate negative y, you get that. So it's pretty nice. With respect to u squared the number gets you 2u the number. Number u gets you the number. If you do it with the v's, you get 2 u squared v. And this guy, you get minus u. Pretty clean one. Right. Be careful with this one. E to the power of mt. That's e to the power of m times a number, right? M's a variable, t is treated as a constant. So you get e to the mt times something. Don't you get the derivative of mt with respect to m, right? So it's a bit like m times a number. So you get an extra t. So this one is t e to the mt. And this guy is e to the mt as well. But when you differentiate this guy with respect to t, you get the m. And so there's a kind of changeover this time. Are we good? Yeah. What I'm saying is kind of true. We are just going to try some combinations of various things. Let's do a chain rule one, just version of question 10. It's a pretty weird looking one. If you differentiate with respect to r, you get 9 cosine of this theta times the derivative of the inside function with respect to r. So if you differentiate this with respect to r, you get a cosine theta. And then you write them down in order of complexity. Simplest at the start, ugliest at the end. And there's your answer. Now, if you do a partial derivative with respect to theta, let's see what you get. You get 9 sine somethings gets you 9 cosines of that something. And then you finish with the derivative of what's inside. And the derivative of this with respect to theta is negative r sine theta. So we are looking at negative 9r sine theta, a cosine of r cos theta. Any questions? Are we good with chain rules? I'm not changing the rules of Calc 1. I'm just adapting them to having 2 variable situations. Let's take something. What shall we do? And interesting here. How about this fella? I'm going to do the partial derivative with respect to y. Now, if you differentiate this expression with respect to y, don't you get a big fat 0? Isn't this just a number? Right, there's no y's involved. And if you differentiate this guy with respect to y, don't you just get the cosine x piece? On the other hand, if I want to do this guy, I'll have to differentiate this and this. Right? That is a product rule, isn't it? So I'm going to do f dash g plus f of g dashed. On the other hand, isn't that guy just like 5 cosine x's? So when you differentiate it, you get negative y sine x. So that is not a product rule, yet this is, right? You see? Differentiate this, you get 1, leave the second alone, leave the first alone, differentiate the second, and then you get, okay. And tidying up, I have a sine x, I have an x cosine x, and I have a minus y sine x. I hope the more of these I do, the more comfortable you are with this concept of partial derivative. Aren't you just differentiating with one variable and just thinking of everything else as a number, right, as a constant? Treat it like a constant and you're going to be safe. Do you know there's no limit to how many variables a function can have? Isn't this function a function of 3 variables? Which means that you can have 3 partial derivatives. How do you think we're going to deal with a situation where there's more than 2 variables? Now there's 3, but there could be 4 or 44. Do you think we're going to make a big change to the process? No. Aren't we just going to say there's 1 variable and everything else is a number? Or treat it at least as a number. So you differentiate this guy, you just get 2x. If you differentiate this guy with respect to y, you just get that. And if you differentiate this guy with respect to z, you get that. Okay. For the last question, I'm going to cheat a little bit. I want you to imagine that I was going to differentiate this guy. And oh, let me do that again. Imagine I have this function. Functions that have a very nice relationship are called symmetric functions. A symmetric function is a function where if you switch the x's and y's, if they switch places, you still have the function you started with. Would you agree if all these x's turned into y's and all these y's were turned into x's, wouldn't it still be that expression when you're finished? That is a symmetric function. Basically, if you switch the x's and y's around, if you want to see what it looks like formally, f of xy is the same thing as f of yx, right? That's a symmetric function, right? Now, can you imagine that you had to differentiate this function? This is the bit where I'm going to cheat or lie, actually. And let's just, for example, say that the answer ends up looking like this. Right? Just pretend that that was the answer. I know it's not, but pretend it is, right? If you fight your way through the first derivative and you get this answer, and the function is symmetric, you can save yourself a lot of work. You can actually predict what the other derivative would be by using symmetry. Now, what that means is switch the x's and y's around, right? So all the x's become y's and all the y's become x's. And that would mean then that if this was the correct answer, you would get 2y squared, take away 4yx, all over yx, the sine of y, the cosine of x, all squared. Does that make sense? It's not a biggie, but would you agree if it was a really horrible derivative, wouldn't this shortcut be really cool? Because it means you don't have to fight your way through some really, really ugly derivative a second time. You can use the answer to this one to predict the answer to that one. And I think we've reached a very natural starting point. And I think my jokes were excellent. I'm not sure you did, but that's not going to affect me in any way in your grading. Although, Kira, I'm sad to say that you've now failed.
It just means I can take your class again. I'm cool.
Okay, have a last name and bye-bye, guys. I will see you soon. I will hang about for questions, of course.
Bye. Have a good rest of your day.
I will try. Chris or Eric or Wendell, do any of you have questions for me? No? Chris, Eric? Maggie, you go on.
Yeah, I do actually.
Okay, let me get a second to tidy up. Okay, I'm ready. What's your question?
All right. So number 6, I think I just wrote down the final answer wrong. Can you?
Question 6 on the section we're on right now?
Yeah, the one we did in class.
Okay, let's have a look at it. I'll switch to the main screen, see what that looks like. So it is x squared plus xy. What number do you have? Is it 100 or something, or 9?
Yeah, you used 100.
I used 100. It's red. It turns into other numbers. Okay, so the partial derivative with respect to x. This is a chain rule, right? So it's going to be 100 the something to the power of 99. You comfortable with that bit?
Mm-hmm.
Right. Now the derivative of the inside function, that's this guy, with respect to x, is 2x plus y. Because x times a number gets you just a number, right? So it gets you the y. And making it look pretty is just a matter of rearranging the order from simplest to ugliest. Any problems with that one?